So let me just remind you what the linearization is about, what the whole story of linearizations are. And I think it's important for us to always, keep in mind in context what's going on here. Why are we studying this? So for the linearization problem, we motivate it this way. Suppose we know f of a and we know delta x. The question is, we now want to find f of a plus delta x. So the answer is, well, we can approximate f of a plus delta x by first finding the tangent line at a and then evaluating the tangent line at a plus delta x. So we end up using the value of the tangent line at a plus delta x as our approximation for the value of the actual function. So that's linearizations. That's the whole thing. We just use the tangent line to approximate the value of the function for values of x near a. That's linearization. And the difference here, so this height difference here between our approximation and the actual, that would be called the error. And of course, the smaller the error, the better, but whatever. So now that's linearizations. So now how do differentials come in? Well, differentials are just an application of linearization. So in differentials, we now want to find this height. So now I want to find f of a plus delta x minus f of a. But the problem is I don't know f of a plus delta x. So what's the answer? The answer is we're going to approximate f of a plus delta x. Instead of using f of a plus delta x, we'll use L of a plus delta x. And our approximation of the height, we'll use this height here. L of a plus delta x minus f of a. And again, the difference in the height is what we call the error. And so that's differentials, just when we use L of a plus delta x minus f of a instead of f of a plus delta x minus f of a. And linearizations is when we approximate f of a plus delta x with L of a plus delta x. Okay. So we then did this example, and we sort of worked through the whole example, but I want to start here, just focus on this third example here. The previous two examples, the techniques from the previous two examples will be used in this third example here to solve this third example. So ignore the first two examples. Let's just focus on this third example, which states, suppose the edge of a cube x increases from 10 centimeters to 10.1 centimeters. Estimate the change in the volume using differentials. So this is a classic differentials problem in that we have some function, here's the volume function, v of x equal to x cubed. And the input of the function starts out at some fixed value, in this case it's 10 centimeters, and then changes. In this case, it increases to 10.1. It doesn't have to increase, it's just, in this case, that's the example. So, there's going to be a change in volume. So now what we're being asked to do, we want to approximate the change in volume. We want to approximate v of 10.1 minus v of 10. We want to, approximate how much the volume is increased or decreased by. So the idea is we're going to approximate delta v, the actual change. So we approximate actual change delta v with the differential dv. And the differential is just when we approximate the new volume with the value of the tangent line using a linearization. So here I calculated if v is equal to x cubed, then by definition, dv is just v prime of x dx. This is the theoretical definition of the differential. And here, v prime of x looks like 3x squared dx. And so now for the dx, dx is just the same as delta x. So here I'm going to take the new value of x and subtract the old value. So here you can see delta x dx, which equals delta x, is 10.1 minus 10, which will equal 0.1. So now we're ready to do our approximation. So the actual change, delta v, which we don't want to calculate due to restrictions on our resources, we approximate with v prime of a delta x, where we plug in the original value. So here a is 10 and delta x is going to be 0.1. And so then, I do the math to finish. So here, remember, for v of x, that gets replaced with 10, the original value, what it started out as. And so we're able to approximate the change in volume is 30 centimeters cubed. So let's be very specific here. The change in volume is plus 30 centimeters cubed. So what we're saying is the volume will increase by 30 centimeters cubed. So there's approximately a 30 centimeter increase when x changes from 10 to 10.1. And if we know how much it's increased by, I can now also approximate what the new volume is. It would be the old volume, v of 10, plus the addition, the increase. So here I can approximate the volume at 10.1 is going to be approximately starting with the old volume, which is v of 10, add 30, because differentials tell us it increases by 30. And here, what we've done here, when we take the old value, the original value, and adding the differential, that's a linearization. So here on the right-hand side, this expression here, v of 10 plus 30, that's actually a linearization approximation of v of 10.1. So you can look at the first example to see the linearization. So differentials are really just about using the tangent line as approximating the new function value. So sometimes we'd like to know what the relative change or relative error. So previously I said the volume increased by 30 centimeters cubed. Is that a lot compared to what we're dealing with here? Is that a little bit? So what we'd like is what's called a relative change, or sometimes called a relative error. So the classic differentials problem is we have some independent variable, starts at some fixed constant a, and then either increases or decreases to this new value a plus delta x. So I start at a, and then I increase or decrease to a plus delta x. So now what we'd like to approximate is the change in the output value, or the relative change in the function f of x, the output function. So this actually goes back to a formula from algebra, way back like 7th grade or 8th grade, when we were trying to calculate what's the percent increase. So if I have an original value, some original number, and then that number gets updated, so what if the new number, how much, what percent bigger is that, or what percent increase did we have? And if you remember the formula from back in the day, the formula is you take the new value, subtract the original value, divide by the original value. That gives you the relative increase or decrease. It'll be an increase if the new value is bigger than the original, and it'll be a decrease if the new value is less than the original. Here in the context here, the new value minus the original value looks like this. F of a plus delta x is the new value minus f of a is the original value divided by f of a, the original value. So here, in context here, relative change in terms of our formulas would look like delta f over f of a. And if you multiplied that by 100%, that would tell you the percent change. So where does calculus come into this? So far, this is all just algebra. So calculus now comes into this because we don't want to calculate delta f. So instead of calculating delta f, we're going to approximate delta f with the differential, which is what we've done, on the previous slide. Approximate the actual change with the differential. And so now if I replace the actual change with the differential, I get my formula here. So this formula here now approximates dF over FA, approximates the relative change or relative error. And then I went ahead and plugged in the formula for the differential. So dF by definition is f prime of a times delta x. So here's our formula. When we put everything together, we come up with this approximation for the relative change. So the relative change when x changes from a to a plus delta x, the relative change in f would be f prime of a times delta x over f of a. You know, one thing I would be careful about is that when you look at this formula, the relative error formula, just by itself, it doesn't really make sense. If you just look at this numerator term out of context, if you just look at f prime of a delta x, that seems weird. You know, that's why I think it's really important to tell yourself the story that, oh, f prime of a times delta x is actually, you know, because we're trying to approximate delta f. And, you know, this all goes back to this formula here, this new value minus the original value divided by the original. So I start with that formula, but then I approximate the numerator with the differential, so I get this weird relative error formula here. That's f prime of a delta x over f of a. And if we just take the relative error and multiply it by 100%, we get what's called a percent change or percent error. So I start again with new value minus original value, divide by original value, but I multiply by 100% because I just want this in terms of percentages. And so we're looking for delta f over f of a times 100%. And as before, instead of actually calculating delta f, we'll approximate delta f with the differential. So the formula for the percentage error now becomes f prime of a times delta x over f of a times 100%. So, you know, this is just like an algebra thing. If something changes from 10 units to 15 units, it increased by 50%, right? So that's all we're figuring out here. That's all we're calculating. We went from 10 units to 15 units. So the increase would be 15 minus 10 divided by 10. You know, 0.5 would be the relative change. Multiply that to get 50% is the percent change. That's all we're doing, just algebra, except we're approximating this part, the difference in the numerator, which, you know, is delta f. We're approximating that with a differential. That's the only difference. So here we have this example that's related to the volume example from the previous slide. So suppose the edge of a cube increases from 10 centimeters to 10.1 centimeters. Estimate the relative error and percentage error in the volume of the cube. So we want to know what's the change in context of the original volume. So I'm just going to approximate. I want to find delta f over f. But since it's too difficult to find, you know, we don't want to do the work to actually calculate f of a plus delta and calculate delta f. So instead of actually calculating delta f, I'm going to approximate it with df, the differential. And so now I plug in the formula. It's f prime of a delta x. Here a is 10 and delta x is 0.1. So I plug everything in and we get my relative change or relative error is 0.03. So there's been a 0.03 increase in the volume. Or if you want the percentage error, percentage change here, if you multiply 0.03 by 100%, we get there's been a 0.03 increase in the volume or a 3% increase. And so this helps us to put things in context. When x increases from 10 to 10.1, that's a 1% increase in x. So here, a 1% increase in the x variable results in a 3% increase in the output variable. You know, so that type of thing is handy to keep track of, especially from an engineering perspective when you're dealing with, you know, fluctuations due to heat or motion. And so these little changes we want to keep track of, potentially using differentials. So I do this last example here. It's a little more abstract. I want to do a slightly trickier example. So here we're given some function p that's equal to k, where k is a constant, times x to the fourth. So p is the output variable and x is the input variable. So the question asks, how will a 10% increase in the input variable affect the output variable? So if I increase the input variable by 10%, will that increase the output variable by 20% or 30%? That's the question here. So I'm going to compare the relative change in P with the relative change in X. Okay, I want to compare those two relative changes. So let me calculate or approximate the relative change in P. So the actual change we approximate with the differential, which by formula is P prime of X dx. Here, the derivative of P of X, so K is a constant, so we just copy the K. So just take the derivative of the X to the fourth part, use a power rule that's 4x cubed. So the derivative here is 4kx cubed, and then dx equals delta x. So that's where we get our differential here. So now the relative change is dp over p, that's the approximate relative change. We're approximating delta p over p. So I plug in the differential in the numerator. So here, this is the differential we calculated up here. And now do some algebra. So I'm going to cancel the k. I'm going to cancel the x cubed, and I'm going to cancel downstairs. I'll have 1x left. So I'll cancel, I have x to the fourth, so cancel x cubed, so you still have x left. So now if you look at this, you have 4 times dx over x. And dx over x, this is the relative error or relative change in the input variable x. And so what we're seeing here is that the relative change in P is equal to 4 times the relative change in the input variable x. So if the input variable increases by 10%, then according to differentials, we can approximate that the output variable will increase by approximately 40%. And so, this type of analysis, I think, is very important in terms of analyzing stresses and strains, or analyzing how will a certain tiny little perturbation on this part of my system affect this part of the system. So to be able to, through chain rule, kind of track all of the changes. Chain rule and, differentials. So that ends the discussion here on chapter 2. And so without further ado, I want to start chapter 3. So it's important that we keep the big picture in mind. So we started by looking at limits, then we defined derivatives, and we learned how to do a derivative, and we learned properties of derivatives. Then we started applications. So related rates was the first application. Remember, we like derivatives because derivatives can model a world that changes and moves, i.e. derivatives can model the real world. Then we talked about linearizations and differentials. So that's, very practical application in terms of literally how do we approximate values of functions. So now all of chapter 3 is more applications of derivatives. The main application is to graphing. So, here when we're graphing the function, it's a geometric application, but when the function actually has a physical interpretation, if we know the graph, that tells us a lot of information about the system. So when it comes to graphing, we're interested in interesting features of a graph. And so for a two-dimensional graph, the interesting features would be things such as x-intercepts, y-intercepts, horizontal and vertical asymptotes, as well as high points and low points. And so high points and low points are called extrema. They're the extreme values of the range. And we have two types of extrema. We have absolute extrema and we have we have absolute extrema and we have local extrema, okay? So in terms of the test next week on Wednesday, the test will cover absolute extrema. Although today I will talk about both absolute and local extrema, the test next week won't cover local extrema. Exam number 3 will cover local extrema. Okay, and I'll explain why in a second. So let's start with the definition of absolute extrema. So we have 2 types of extrema: absolute maximum, the high point, and absolute minimum, the low points. So we say there's an absolute maximum at the point x equal to c if and only if, you remember what if and only if and only if f of x is less than or equal to f of c, and this is the important part, for all x in the entire domain of f of x. So we're looking for a range value, f of c, such that it's the largest range value. All the other range values are less than or equal to this range value. And the place on the x-axis where this highest point is happening is called the absolute max. The actual value of the highest point is called the absolute maximum value. So we're distinguishing here between the x and y coordinates of the maximum. The x coordinate is called the absolute maximum, and the y coordinate corresponding to that absolute maximum is called the absolute maximum value. And similarly, we have the idea of an absolute minimum. And again, the important thing in the definition here is we have an absolute minimum of x equal to c if and only if f of x is greater than or equal to f of c for all x in the domain of f of x, in the entire domain. So that's why we use the phrase absolute here. It's like an absolute ruler, you know, it's the absolutely the smallest of all the range values in the entire domain. And again, we distinguish between the x value where this minimum is happening. So the x value is called the absolute minimum, and the corresponding output, the y value, is called the absolute minimum value. So these are absolute extrema. So these are the highest points over the entire domain. What we would like to also define is a less strict idea where it's not necessarily the highest point in the entire domain, but it's maybe the highest point, like it's a little hill. It's just the highest point compared to all the points around it. Or it's a little valley where it's the lowest point, not necessarily compared to every range value, but it's the lowest point just compared to the points around it. And so those are called local because we don't need them to be the highest or the lowest. We just need them to be larger than the points around it or less than or equal to the points around it. And as before, you know, local extrema, we have 2 types of extrema, local max and local min. So here for the function, f of x has a local maximum. And again, we distinguish in terms of the terminology between the x and y value. So the x value where the local max is occurring is called the local maximum. In its domain, if there exists an open interval containing c, so this part's important. This part is what makes it local. I'm not saying for all domain in the function, such that f of x is less than or equal to f of c. And again, for double emphasis, I wrote it down. For all x, not in the entire domain, that would be absolute, but just in some open interval containing c. So what's an open interval containing c? You know, if you have your x-axis like this, and if this is the point c right here, we're just looking very close, very, very close at the left and right side of c. And for it to be a local max, the function would have to peak at c and be the highest point at c. So, and again, you know, the actual y value is called the local maximum value. And I'm going to highlight this again just for emphasis, that it's not for all x in the domain, but that it's for all x in some open interval containing C. That means it's for all x just very close to the left and to the right of C. Similarly, we can define the local minimum. Again, it has to be the lowest point, not for every y value in the range, but for all x in some open interval. It just has to be the lowest point compared to the x values next to it on the right, as well as to the x values on the left. And the actual number, the y value, is called the local minimum value. So based on these definitions of local extrema, the first thing I would really emphasize is, based on this definition, just by definition, local extrema never occur at endpoints. By definition here, local extrema have to be inside the domain, because we need to be able to check how are the points on the left and how are the points on the right. For local max, I need to check that the local max is bigger than the points on the left and the right. For local min, I need to check the points are less than all of the values on the left and the right. So both sides, so you can't have it at an endpoint. So here I have the graph of 5x cubed minus 3x to the fifth. This graph has no absolute extrema. On one end, you see the graph goes to plus infinity. On the other end, you see it goes to negative infinity. So as far as the range goes, there is no largest value of the range. There is no smallest value. However, this function does have local high points. As you can see, at x equal to 1, we have a little high point. There's a little hill here, and at x equal to 1, f of 1 is not the largest range value, but it's the largest in a small interval around 1. So starting at 1, if I look at a small interval around 1, and you ignore everything outside of this interval, you can see f of 1 is the highest point. And again, at negative 1, we have not an absolute min, but a local min. It's a point where the y value is less than or equal to all the y values around it to the left and to the right. When you're talking about these local extrema, we're really close to the point to the left and the right, and you can basically ignore the rest of the function. Here, I'm not really concerned with what's happening away. All I care about is what's happening to the left and the right of negative 1. If f of negative 1 is the lowest point, which it is, then it's going to be a local min. And so here we have a local min at x equal to negative 1. If you want the local min value, I would plug in negative 1 into the function. So the local min value would be negative 5 plus 3, or negative 2, doing some quick math. And we have a local max at 1. The local max value would be 5 minus 3, or 2. And this graph has no absolute extrema at all. It only has the 2 local extrema. So as I said, we will learn how to actually classify and find local extrema in section 3.3, which will not be covered on exam 2. Okay, so local extrema, even though I've given you the definition today, you're not responsible for it for the exam on Wednesday. So I just want to now give you some examples, what I call oddities of extrema. And these are good examples just to help us think about how local and absolute extrema work. So the first example here, I like this one because this is an example where you have no local min. So here, this does have a absolute min, it does have an absolute max, and it does have a local max. So the absolute min would be right here at the endpoints. The absolute max, which is also the local max, would be right here at the top, at the very top. That's your absolute max as well as local max. Now there are no local min. And the reason is, for example, if you go to this endpoint, if you go down to the x-axis. And if you look to the left and right, I cannot conclude this is the lowest point for all points in the function from the left and the right, because here on the right side, there's no function definition. The function's not defined. I can't say this is the lowest point in an interval around it. So at the endpoints here, we only have absolute minima. So if you flip this picture, we get the opposite situation. This is a graph that has no local max. This does have an absolute max. These endpoints here are absolute max. And this does have a absolute min, which is also local min right here at the lowest sag point of the graph is both a local min and an absolute min. This next graph has no local extrema at all. This next graph has only absolute extrema. So on the right-hand side here, we have the absolute max. And on the left-hand side here, we have the absolute min. There are no local extrema. So let me explain that. So if you pick any point that's not an endpoint, so if I pick a point right here, let me make it a little smaller. So pick this point right here, kind of in the center-ish. For, what we're looking for is if you go down here to the x-axis, I want to check to the left and to the right, is this point that I've picked, is that either greater than or equal to all of the points to the left and the right, or is it less than or equal to? If it's not either of those, then it's not a local max or min. And here you can see that since the function is always increasing, if you look at it from left to right, there are no local little bunny hills, there are no little valleys. So here, only absolute extrema at the endpoints. This next one I like a lot, because here's an example of a function that has no extrema of any kind. The endpoints are not colored in. So technically, this function, because it's defined on an open interval, has no highest point. For example, suppose this number down here, suppose this is a 1, and suppose this number up here, so that's a 2. The range here would look like open interval 1 to 2. That's what the range would be. And this doesn't have a highest or lowest value. Any number you pick, I can always get a little closer to 2. So I say 1.9, well, I say 1.99. And then the next person says 1.999. And the next person, so any number you pick, you can't pick 2 because 2 is not in the range. You can get as close to 2 as you like, but you can't get to 2. So here there's no largest number and there's no smallest number. So there's no absolute extrema. And because of the diagonal part in between, there are no local extrema. There are no local little bunny hills. There's no local little valleys. So no extrema of any kind, but this is a bounded function. What do I mean by that? The range is finite. The function isn't blowing up to infinity or negative infinity. You compare with the graph of x cubed. Again here, we have no extrema of any kind. There are no local or absolute extrema here. But in this case, the function is what we call unbounded. That means, you could have, unbounded means you have either infinity or minus infinity in the range. In this case, we have both infinity and minus infinity are in the range. So here we have two examples of functions that have no extrema, but one is bounded, one is unbounded. And the last example I like here, it's kind of a non-example. Here, every point in between, every one of these points is a local max, a local min, and an absolute max and an absolute min. So here, all the points in between are every kind of extrema. Why is that? So one little subtle point to keep in mind is in the definition, we allow equality. We don't say for it to be a local max, it has to be strictly greater than all of the other y values. We say greater than or equal to. Again, for the local min, we allow equality. Similarly, for the absolute max and absolute min, we allow equality. So here, for this very trivial case of this horizontal line where the endpoints aren't colored in, all the points in between are every kind of extrema. Local max and min, absolute max and min. But of course, this is the most boring function. We wouldn't need any fancy calculus to analyze this function. It's a very straightforward and boring function. So if I color in the endpoints, be careful, if I color in the endpoints, then the endpoints will be, both endpoints will be both an absolute max and an absolute min, but the endpoints will not be local extrema because we don't allow local extrema on the endpoints. Okay, so I went with not coloring it in, so now I can say everything in between here, these are local and absolute extrema of both kinds. So we get some theorems now just to kind of try and describe function behavior. And we know one really, really nice situation where nothing can go wrong. If the function is continuous, so that's one property, you have a continuous function on a closed interval, then this function has to have an absolute max and an absolute min somewhere. So let's think this through. The continuity tells us that the function has to be defined at every point, because continuity says limit of f of x as x approaches a equals f of a. To be even able to write down f of a, that means a is in the domain of f. That means f of a is a finite number. So here, if the function is continuous on the closed interval, this is including the endpoints, you know, continuous from the left and the right. This means at every point in the closed interval, the function value is a finite number. It's not blowing up to plus or minus infinity. It includes its endpoints, so it must have an absolute max or min somewhere in the interval. Fermat's theorem says, if f of x has either a local maximum value or a local minimum value at some point in its domain, and if the function is differentiable, then f prime of c must be 0. So what this is saying is, if the function is differentiable, we can't have a maximum value that looks like this, that looks like a, you know, a cusp type thing. Because if you say the function is differentiable and it has a maximum, then when it goes up to a peak, it has to be a nice differentiable peak. And so if it's differentiable and it has a local max or min, then where it has a local max or min, it has to be a horizontal tangent. For differentiability, the picture has to look like one of these two for differentiability. If we remove differentiability, if you say, okay, well, what if it's not differentiable? Then you could get something like this. You could have a max, or you could have something like this where you have a min occurring. Both these examples do tell us something, though. They do shed light on, in general, where might we expect an extrema to happen. It looks like you might expect an extrema to happen where the derivative is 0, where there's a high point, or, you know, like a nice hill or valley, or where the derivative is undefined, because that's what we see from these experiments here. Okay, so we give a number that makes either the derivative 0 or undefined. We give that number a special name. We call any number that's in the domain of the function that makes either the derivative 0 or undefined, we call that a critical point. And critical points are where we suspect extrema happen. So I say suspect. Once we find critical points, we then need to classify them. We then need to check, is there actually an extrema happening? Remember, Fermat's theorem is not an if and only if. Fermat's theorem says, if we have local extrema and if the function is differentiable, then it's going to have horizontal tangents. It doesn't say if it has a horizontal tangent, then we for sure have local extrema. So critical points are one of the first places we're going to check to see if there are extrema there. And when I say check, I'll tell you how we check. So for right now, as I said, we're going to focus on absolute extrema. So to find the absolute extrema of a continuous function on a closed interval, first we need to find all critical points of the function. So I'm going to find the derivative, figure out where the derivative is 0 or undefined. And but I need to make sure where it's 0 or undefined, those are still points in the domain of the original function. Then I'm going to evaluate the value of the function at the critical points. What does that mean? I'm just going to find the corresponding y value for each critical point. So I'm checking the values at the critical points. Extrema can also occur at the endpoints. So I'm also going to check the value of the function at the endpoints, i.e. I'm finding f of a and f of b. And now the largest y value from steps 2 or 3 is the absolute maximum value of the function. And the smallest value from step 2 or 3 is the absolute minimum value. It's a very straightforward process where we're literally checking the height at the endpoints A and B, and we're checking the height at the critical points, at the points that make the derivative either 0 or undefined. The highest height is the absolute max value. The lowest height is the absolute min value. Let me just make one comment. The book only talks about closed intervals. I want to talk about what if you have an infinite interval or half closed. So for an interval like this, minus infinity to infinity, or a to infinity, or negative infinity to b, we do the same procedure, but when it comes to checking the endpoints, so when it comes to step 3 here, which is evaluate f of x at the endpoints, the way we do it here is we would use a limit. If your endpoints are like plus or minus infinity, then the only way to quote unquote check the endpoint is to take a limit. So we take the limit of f of x as x goes to plus infinity and minus infinity as necessary. If the limit blows up to infinity or negative infinity, then there's no absolute max. If the limit equals a fixed number, then we check, is that the largest number? Is that the smallest number? But if it blows up to plus or minus infinity, there are no absolute extrema. So let me do one last example here and stop. We have about 7 minutes. So I think I just have enough time this is a find the absolute extrema problem. But I've broken it up into 2 steps because every extrema problem has one thing in common. For every extrema problem, you'll always be finding the critical points. Whether I'm looking for absolute extrema or local extrema, I'm always going to first find the critical points. And then once you find the critical points, you try and figure out what's going on there. So here I start with the example here is to find the critical points of the function f of x equal to positive square root of 4 minus x squared. Remember, the critical points are numbers in the domain of the original function that make the derivative 0 or undefined. So I just want to make sure I know what the domain of the original function is here. Here, because this is an even root, I need what's under the root to always be greater than or equal to 0. So here I need 4 minus x squared to be greater than or equal to 0. And now I'm solving this. I'm trying to find x values that make the left-hand side positive. And by plugging in, you can show x equals, x is between -2 and 2, or you can graph it. I actually just like to graph it. Here, the graph of 4 minus x squared, so minus x squared flips the parabola around. And when you add 4, it moves it up 4 units. And here you can see between -2 and 2, the function will be positive or non-negative. And so that's where my domain is coming from. Either way, we should be able to solve it both ways, graphically, algebraically. So now let me find the derivative. So for positive square root of 4 minus x squared, I'm first going to write that as 4 minus x squared raised to the 1/2, because that's the form I have a rule for. And the second thing, so this part's really important, is I go, oh, this is a derivative problem. and I'm trying to find the derivative of a composition. So I'm going to need to use the chain rule. And here the inside function is 4 minus x squared. The outside function is being raised to the 1/2. So the derivative of something raised to the 1/2 is 1/2, copy down the something, which is 4 minus x squared, raised to the 1/2 minus 1. 1/2 minus 1 is negative 1/2. That's where this is coming from. Then chain rule times the derivative of the inside. The inside is 4 minus x squared. The derivative of 4 minus x squared is 0 minus 2x, or just 2x. So here's the derivative. Now, one very important thing I want you to notice and to think, that I want you to think that, aha, because this is a negative exponent, this entire term is actually a fraction and is in the denominator. So that part I want you to notice and to be very aware of. And so now when I rewrite it, put that thing in the denominator, this is the derivative. And now I'm asking myself, where is this expression? When is it equal to 0? And when is it undefined? For a fraction is always equal to 0 when the numerator is equal to 0. So I know the derivative will be 0 here when x is 0. So that, and x equal to 0 is in our domain. So that's a critical point. Remember, our domain is -2 to 2. And now I'm asking myself, when will this derivative be undefined? Well, notice that this is a fraction, and fractions are undefined when the denominator is 0. So now I'm wondering, okay, what happens to this function when x equals 2 or -2? You know, the only thing I'm worried about is it some kind of removable thing happening? Here we know that if you plug in 2 or -2, you get a non-zero number in the numerator and 0 in the denominator, so nothing's going to cancel. This is not removable. But to be, you know, perfectly mathematical and perfectly correct, I went ahead and took a limit. As x goes to -2 and as x goes to 2. Remember, the domain is -2 to 2. So I can only take a limit as x goes to -2 from the right. So that's what I'm doing here. If you plug in the -2, so we're plugging -2 into this function, the derivative. Plug in a -2. In the numerator, you have -2. I have a number over 0. I get 2 over 0. And if you check the SIGN, the denominator is always positive. Here you have this minus sign, and x is going to -2. The 2 minuses cancel. We get plus infinity. Similarly, I take a limit. So that says you have a critical point. That says the derivative is undefined at -2, but -2 is in the domain. Similarly, I do the same thing for 2. Take the limit as x approaches 2. Here, I can only take the limit as x approaches 2 from the left. If you look at the domain, plug in the number, you get number over 0. And if you check, because the denominator is always positive, this minus sign, and since x is approaching 2 from the right, from the left, you know, x is very close to 2, x is positive, this whole thing is negative. So we get a negative infinity. That is to say, we have, you know, because these points are in the domain, we have the critical points are -2, 0, and 2. So the whole point, the whole reason I found the critical points was so that I could do this next example here, where we will find the absolute max and min of the function. All that's left for me to do is check the value of the function, check f of x at the endpoints. And here I was trying to be sneaky. So here one endpoint is -2. But I gave the other endpoint as being 1. Just in the problem, I said let the function be defined on -2 to 1. So we need to check the function value at -2, at 1, and then also at the critical points, -2, 0, and 2. So here -2 is both an endpoint and a critical point. All right, I'm not going to do this example. I'm going to stop right here and continue with this example next time.